Assalamualaikum and a very good day everyone. So in this video I will cover topic for power supply circuit. So for this topic it's actually for week 10 and I will give introduction first. So electronic circuit, all electronic circuit, they need power source to function, right? So power supply is a unit, is a supply unit. Power supply unit is a device used to convert, regulate and transmit the required power to the circuit to be operated. So electronic circuit made up of semiconductors, they need specific value of direct current or DC voltage, and batteries are common DC voltage source for electronic equipment, especially portables like cell phone and iPod. And most non-portable equipment uses power supplies that operate from the AC power line but produce one or more DC output. So there are several power supply characteristics. The first one is the input voltage. The input is 240 volt and 50 hertz alternative current, or we call it as AC. And then a power supply unit converts the alternative current to direct current and provides one or more DC output voltages. And some modern electronic circuit, they need two or more different voltages. So commonly required DC voltage are 48, 24, 15, 12, 9, 5, 3.3, 2.5, 1.8, 1.5 and 1.2, and also 1 volt. And a good example of modern power supply is one inside a PC that furnishes 12, 5, 3.3 and 1.2 volts. So the operation of DC power supply circuit, the importance of DC power supply units in all electronic appliances is that power supply provide one or more fixed voltages with sufficient current to the operating circuit. And then electronic devices such as transistor radio, television, video, CD players, they operate fully or partially on DC power supply in the range of 0 to 24 volt. And the successful operation of the device depend on the proper function of the DC power supply. So the power supply tries to provide a smooth and constant DC voltages as required by electronic devices. So major electronic appliances have built-in electronic circuit that take power from a wall socket and convert it to the form and voltages required by the other internal circuit of the appliance. So here is a block diagram of DC power supply. So we will take the AC or the mains of 230 to 40 volt and 50 hertz, and then we fit in transformer and then go to rectifier, filter, regulator and voltage divider, and then to load. So the function of each of this block is to provide DC power supply. Okay, the first one is we have the AC voltage, and then at the end, after voltage divider, we will get the regulated smooth DC supply. So the AC voltage will go through the transformer, so that and then the function of this transformer to step down the high voltage AC to a lower voltage AC voltage. And then after this block, we will get a low AC voltage, and then the low AC voltage will pass through rectifier and it convert the AC to DC, but the DC output is still varying, and then the output from the rectifier is pulsating type. And then we will use filter to smoothen the DC from varying greatly to small ripple. So now we already have the small ripple here, not like pulsating type. So this is unregulated voltage. Okay, and then we will go to regulator to eliminate the ripple here by setting DC output to fixed voltage, and finally I will pass through voltage divider to divide DC voltage, which are different needed value circuit. So we will come up with the regulated smooth DC supply. So transformer, we will look at the detail of transformer. So this is the symbol for transformer, and then this is the real picture of the transformer. So we know that there's two coil here, the primary coil and secondary coil. And then for the first coil, we have the input, which is the high voltage AC, which is the main supply, and then the secondary coil we will get the output or low voltage AC. So here the transformer here, the function is to step down high voltage AC to low voltage AC. So you can see that the primary coil is greater than the number of coil in the secondary coil. So transformer is commonly used to step down input AC voltage to a lower level. You know the function of transformer, you can be you can step up the voltage, or you can step down the voltage. So but then here the function is to step down the input AC voltage to a lower level. So for example, a transformer with a turn ratio of 10 to 1, meaning that 10 is the primary coil, the 1 is the secondary coil. So you know that it is a step down transformer. That will convert the 240 volt 50 Hz input sine wave into 25 volt sine wave. And then for low voltage AC output is suitable for lamps, heaters, special AC motor, and then it is not suitable for electronic circuit unless they include a rectifier and a smoothing capacitor. So here you can see that the input here is the high voltage AC, the blue line here, and then the output is the low voltage AC. Then after the transformer, the voltage will pass through the rectifier. So we will look at what rectifier will do. Here the function of rectifier is to convert AC to DC, but DC output is still varying, meaning that after the voltage pass through rectifier, they will come out with a pulsating type of voltages. Okay, so this is the symbol for rectifier, and then this is the real image of the rectifier. So here is transformer connected to rectifier, so we have transformer plus rectifier to get the output. Okay, there are several forms of rectifiers, but all are made up of diode. So we have 4 diodes in the rectifier, and the rectifier, as I've mentioned just now, the function is to convert the AC sine wave into pulsating type DC wave. So you can see here the input is low voltage AC, the output from the transformer just now, right? The orange color, and then after the voltage pass through the rectifier, they will get the varying DC voltage here after, and then there are, if you can see here, there is single diode rectifier produce a half varying DC, but with 2 or 4 diode they will produce a full wave varying DC, meaning that you can see the orange shape here. You have one here, and then flat, and then again, and then flat again, and then you have the value of the output varying DC again. And then but then with 2 or 4 diode you have full wave varying DC. We will discuss a bit more about rectifier later. So after rectifier, the voltage will pass through filter, so transformer, rectifier and filter, and the function of filter just now is to smoothen the DC from varying greatly to a small ripple. So we will have the unregulated voltage output after they pass through filter. Alright, so with filter, okay, filter, the rectifier produce a pulsating DC, unlike a constant steady value that is produced by a battery. So rectifier, they produce a pulsating DC, unlike a constant steady value that is produced by a battery. So pulsating or varying DC output will pass through the filter, and we will have a steady value of DC output. And then you can see this orange line here, the output is a smooth DC, and a filter is then used to remove the pulsation and create a constant output. Here the pulsating or varying DC output, and then here with the filter we will have the constant smooth DC output. Here you can see the straight line here. And then the most common filter is the large capacitor. We use capacitor as a filter, and the filtered DC output have a small ripples, and it is suitable for most electronic circuit. So there's small ripples here, as you can see here, and after the filter we will use regulator. So the function of regulator just now is that to eliminate the ripple. Just now after filter, after using filter, we will have small ripple, and to eliminate those ripples we will use regulator by setting DC output to a fixed voltage, and we will come out with regulated smooth DC supply. Alright, so transformer, rectifier, filter, this is a symbol for filter, and then this is a symbol of regulator, and then this is the real picture of the transformer, rectifier, filter and regulator. And the circuit for transformer, the combination of transformer, rectifier, filter and regulator is as shown here. Alright, so the regulator is a component that helps to maintain a fixed or constant output voltage. Okay, so in regulator they have 3 terminal, in, ground and out, and then it will eliminate all these ripple, small ripple. Okay, so there are changes. The function of regulator also changes in the load or the AC line voltage will cause the output voltage to vary. Okay, so here you can see our output now is a straight line here, a clear line, a clean line, and then most electronic circuit, they cannot withstand the variation since they are designed to work properly with the fixed voltage, and then the regulator fixes the output voltage to the desired level and maintains that value despite any output or input variation. Alright, the regulated DC output is very small with no ripples, and it is suitable for all electronic circuit. So this DC output is very small with no ripples. Okay, so there are 3 types of rectifier. I mentioned to you, we will discuss a little bit more about rectifier. We have half wave rectifier, we have full wave rectifier, and also bridge rectifier. Okay, so this is the shape of rectifier. You can see that with the half wave rectifier we have only 1 diode. Full wave rectifier we will have 2, and the bridge rectifier we have 4 diode here. Okay, now we will look at the first rectifier, which is the half wave rectifier. So the positive cycle operation. During the positive cycle, okay, there is one positive cycle of the rectifier, the positive cycle of the input signal. Okay, this diode is first, it is forward bias, and then diode act as a closed switch, and the current flow through this diode in one direction. So the output drop at RL is the same as the input signal as at positive cycle magnitude. The output voltage keep the shape of the input voltage. All right. And then during the negative cycle, of the input signal, the diode this diode is reverse bias. So the diode acts as open switch. Just now it acts like a closed switch. Now it act like open switch, so there is no current that flow through this diode, and the voltage drop at RL is 0. Just now the voltage drop here is same as the input signal at the positive cycle of magnitude. Now when it is during the negative cycle, the diode is reverse bias, and then the diode acts as open switch, and then there's no current that flow through diode, and from that there's the voltage drop is at RL is equal to 0. So half wave rectifier, the value of the diode is 0.7 volt, and then our V in, for example, our V in is 20 volt, and then after passing through this diode, we will reduce by 0.7, and then our V out is 19.3 volt. So you can see here, this is our input is the alternating current, and then after passing through the rectifier, we will get past DC output here. Okay, and then the calculation of the output voltage, our output voltage for the half wave rectifier is for the positive cycle only, because during the negative cycle the diode acts as an open switch. So the calculation is our V in is equal to 20 volt, and our V out is our V in minus 0.7 volt from the silicon diode. So we will have 19.3 volt. So the output signal frequency is the same frequency as input. So the second type of the rectifier is a full wave rectifier. So full wave rectifier, we know that we have the AC input signal, and that will pass through transformer, and then it will pass through rectifier. So there's 2 diode here, meaning that this is a full wave rectifier. Full wave rectifier, and then the output from the full wave rectifier, we will see all the signal are going up, there's no signal at the bottom part. So a full wave rectifier is exactly the same as the half wave rectifier. It uses two diode D1 and D2. So it allows unidirectional current flow through the load during the entire sinusoidal circle. So it's opposed to only half of the cycle in the half wave. So it is the same like the half wave rectifier. We will have the positive cycle and the negative cycle. Alright. And then during the positive cycle, the M terminal here become positive, and this G here becomes 0. Okay, this M terminal become positive, and then G becomes 0, and N become negative here, whereas N is here, N become negative. So the diode D1 is forward bias, while diode D2 is reverse bias. Okay, so the current will flow through M, and then D1, and then go to A, RL, the load resistor, and then going to G. This is when during the positive cycle operation. Okay, so the input is the same. The input is the alternating current, and our output is this one. Only the positive part of the signal. Okay, so and then during the negative cycle operation, during the negative cycle, this M terminal just now it become positive when during the positive cycle. Now during the negative cycle, this M terminal they become negative, and then G become 0 again. That's the same, and N become positive. Just now N become negative. This N here become negative, but now M become positive, N become negative. M become negative and N become positive, and then at this time D2 become forward bias and D1 now become reverse bias. Okay, just now D1 is forward bias, D2 is a reverse bias, and now when D2 is forward bias, D1 is the reverse bias, the current will flow through N, D2, C, B, and RL and G. Okay, the output wave is always positive now because the current that flow through the load resistor has the same direction for both positive and negative cycles. So now full wave rectifier here, we will have all the current become positive, the output voltage become positive now. Okay, so for full wave rectifier, the shape is like this. The output voltage is formed at both cycle, and the frequency of the output voltage, the frequency of output is twice of the input frequency. And then we will come to the third type of rectifier, which is bridge rectifier. Here you can see the shape here. We have 4 diodes overall, and then after the transformer we will connect this circuit to the rectifier. So we call this as bridge rectifier because we have like these 4 diodes here. And during the positive cycle operation, the bridge rectifier will use 4 diodes, which is D1, D2, D3, and D4. And during the positive input cycle, meaning the positive input cycle, that the signal will pass through D1 here and D2, D1 and D2. D1 and D2 they become forward bias, but then D3 and D4 they become reverse bias. So then the current will flow along G here, and then they will go through G and D, and then D2, C, and then N, M, A, D1, B, R, L, and G. So you pass from here to here, 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 here. Okay, so bridge rectifier during the negative cycle operation, okay, during the positive cycle, we will use D2 and D1. D2 and D1 become forward bias, but then during the negative cycle, D3 and D4 they become forward bias now. Okay, during the negative input cycle, D3 and D4 become forward bias. Just now during the positive cycle, they become reverse bias. But now they become forward bias. So D1 and D2 they are reverse bias now. So from that we know that the current will flow the other way, which is along the G, and then D3, A, M, N, C, D4, B, RL, and also G. Okay, and how to calculate the output voltage for the bridge rectifier? The output voltage become Vp is equal to Vp minus 1.4. So the Vp out equal to Vp SEC minus 1.4. So Vp out is the stand for the output voltage of the bridge rectifier, and Vp SEC is the secondary voltage of the transformer, Vp secondary. Okay. The formula suggests that the output voltage Vp out is the secondary voltage Vp secondary minus 1.4 volts. So the subtraction of 1.4 volts takes into account the voltage drop across diode in the bridge rectifier during rectification. So this 1.4 volts is an approximate value, and it is associated with the forward voltage drop of the diode when conducting. So in practical term, if you know the secondary voltage of the transformer Vp seg, you can use this for the secondary. You can use this formula to estimate the output voltage Vp out of the bridge rectifier. And the reason we use bridge rectifier compared to a full wave rectifier is because the PIV is a lot smaller. So PIV is equal to Vp out plus 0.7 V. So PIV stand for peak inverse voltage. Okay, PIV stand for peak inverse voltage. Okay, so in center tap of full wave rectifier, the PIV across each diode is equal to the maximum secondary voltage of the transformer, which is Vp as secondary. So this is because during the negative half cycle of the AC signal, only one diode conducts, and it has to withstand the entire secondary voltage. However, in bridge rectifier, during the negative half cycle, the two diodes conduct in series. As a result, the PIV across each diode is reduced to half of the transformer's maximum secondary voltage. So the formula for PIV in bridge rectifier is PIV is equal to Vp out plus 0.7 volt, which Vp out stand for the output voltage of the bridge rectifier, and 0.7 V is an approximate value for the voltage drop across the conducting diode. So this reduction of PIV is significant advantage as it allows for the use of diode with a lower voltage rating, potentially reducing the cost and improving the overall efficiency of the reliability of the rectifier circuit. So here is the circuit diagram for the half wave, full wave, and bridge rectifier, and from here we can see the parameter, the number of diode. There are different parameters for the element of number of diode, average DC circuit, average DC voltage, RMS circuit, and also DC power output, and it is related to the number of diode that each of these rectifier has. Okay, so this is just a summary here, and then the comparison between these two diodes you can read from here. The comparison between 2 diodes rectifier and 4 diodes rectifier. For full wave rectifier using 2 diodes, they have it uses center tap transformer. For full wave rectifier using 4 diodes, they use it does not use center tap transformer. So for the 2 diode, 1 diode conduct in each half cycle of the input. For 4 diode, 2 diodes conduct in each half cycle of the input, meaning in one cycle 2 diodes operate for the 4 diode rectifier, but for 2 diode rectifier only 1 diode will conduct in each cycle. And for 2 diode, the voltage drop across the diode is due to the RF only. Meanwhile, for the 4 diode, the voltage drop across the diode is due to 2R. And then for 2 diode, the output voltage is more. For 4 diode, the output voltage is less. And then for 2 diode, the transformer is less effectively used. And for 4 diode, the transformer is used more effectively. And So for full wave rectifier with two diodes, the TUF or the transformer utilization factor is 0.693, but with four diode, the transformer utilization factor is 0.812. So transformer utilization factor TUF is a measure of how effectively the transformer is utilized in a rectifier circuit. So it's defined as the ratio of the DC power output to the maximum AC power rating of the transformer. Okay, for a center tap full wave rectifier using two diode, the TUF indeed approximately 0.693, meaning that about 69.3% of the transformer's secondary winding is effectively utilized. For bridge rectifier using four diode, the TUF is higher, which is 0.812, as I mentioned just now. So this indicates that the bridge rectifier configuration is more efficient in utilizing the transformer compared to the center tap full wave rectifier. So the higher TUF or transformer utilization factor, the bridge rectifier, is because it uses both half of the AC cycle, allowing more continuous utilization of the transformer's secondary voltage. So in contrast, the center tap full wave rectifier only uses one half of the AC cycle at a time. So higher TUF generally desirable, as implies more efficient use of transformer, reduce wastage of power, and making the rectifier circuit more effective in converting AC to DC. And then the last one is the PIV rating of diode is 2 volt for the full wave rectifier using 2 diode, and for the one with 4 diode, the PIV rating of the diode is V, only V, not 2V. Okay, so and then after we feed the voltage into the transformer, rectifier, filter, and regulator, then the voltage will pass through one more element, one more component, which, oh, this is filter, sorry. So after rectifier, the voltage will go through filter. So we will discuss again more about the filter now. So the output of rectifier circuit is pulsating DC voltage, and the resulting pulsating DC signals move of the output voltage. We use filter circuit, and the main function of filter is to convert the pulsating DC voltage into ripple, there's small ripple of DC voltage L, or as good as pure DC voltage, and the free form pulse, which is similar to the value obtained by the battery. So however, not all filter can produce pure DC voltage. The output voltage from filter normally is not really stable. The voltage is mixture of DC voltage with an AC voltage with ripple voltage here. So you can see from this figure 5.52, there is a pure DC voltage, and for the ripple and for figure 5.5.3, this is actually a ripple DC voltage with some ripple here. So the schematic diagram of simple power supply unit, which include the bridge rectifier, filter, and IC voltage regulator. So here we can see that the output is changing from the AC signal into the regulated DC, from the low voltage AC, and that it will pass through the transformer. We will get the varying DC, and then after filtering, we will get the smooth DC, and then after regulator, we will get the regulated DC, which is a clear signal of the direct current. So DC linear power supply, this is a summary of what we discussed just now. We have transformer, we have rectifier circuit. So from rectifier, we have 3 types of rectifier, which is half wave rectifier, full wave rectifier, and bridge rectifier, and then we will pass the signal into filter circuit. We have a different type of circuit here: capacitor filter, RC filter, LC filter, and also pi filter. And then we have some type of regulator. As you can see here, Zener diode, 3-rail transistor. They are example of the regulator circuit, and it will pass to voltage divider. So after that, we will get a clear or clean DC signal. So this is what we will cover, what we will look at in this topic of the power power supply circuit. So just remember that your power supply from the of what we get is AC, but then we need to convert to DC so that we can use it to switch on our to use our appliances, because appliances we use direct current DC power supply. And then there is some component that the AC signal need to pass, which is you need to remember transformer, rectifier, filter, regulator, and voltage divider. And you know that each of these has different function in order for us to get the final regulated smooth DC supply at the end here. So I think that is all for today's for this topic. Okay, thank you so much.